Hi. Today we're going to solve a partial differential equation, namely the heat equation, which says the first partial of u with respect to t equals the second partial of u with respect to x, where t is going to be greater than or equal to 0, and 0 is less than or equal to x is less than or equal to 1. We have one initial condition, which says u of x comma 0 will equal f of x for some f of x. We have two boundary conditions, which say u of 0t will equal 0 and u of 1t will equal 0. And we're going to use separation of variables. So in that regard, let's let our u of xt equal capital X of x and capital T of t. All right, well, plugging this into our heat equation will yield xt prime equals x double prime t. Now dividing both sides by xt will get us x double prime over x equals t prime over t, which must equal some constant, simply because on the left here, this is strictly a function of x. On the right, this is strictly a function of t. Therefore, they have to be equal to some constant. And notice, if we allow f of x to not be identically 0, this immediately implies x and t are not identically 0. If either one was identically 0, this would violate our initial condition. And this allows us to divide by xt right here. Okay. Well, writing out each of these, now there'll be two ordinary differential equations now. One in x and one in t. We'll have x double prime minus cx equals 0. And t prime minus ct will equal 0. Well, we're going to have three cases depending on what c is. Case 1, let's let c be greater than 0. What'll that get us? Well, our solving this ODE then will give us x of x will equal a1 e to the square root cx plus a2 e to the minus square root of cx, where a and 1 and a2 are constants, and t of t will equal a3 e to the ct. Well, our first boundary conditions will say 0 equals x of 0 t of t, which equals a1 plus a2 times a3 e to the ct. But now, since t is not identically 0, that means a3 cannot be 0. This implies right here that a1 plus a2 must equal 0. Similarly, our second boundary condition says 0 is equal to x of 1 t of t, which equals a1 e to the square root c plus a2 e to the minus square root c times a3 e to the ct, which will imply a1 e to the square root of c plus a2 e to the minus square root of c equals 0. And solving these two equations for a1 and a2 will yield a1 equal a2 equals 0. Well, this implies that capital X is identically 0, which was a trivial solution which we eliminated. Okay, case 2, c equals 0. Our capital X becomes a1x plus a2, and our capital T becomes just a constant a3, which of course can't be 0, otherwise capital T would be identically 0 again. Well, plugging in our boundary conditions again will yield 0 equals x of 0 t of t, which equals a2 times a3. Now, since a3 is not 0, this implies a2 must be 0. Our second boundary conditions will say 0 is equal to x of 1 t of t, which equals a1 a3, which implies, again, a1 must be 0. Again, this implies capital X of x must be 0, a trivial solution, which we eliminated. Okay, case 3, c less than 0. Solving our ODE in x will yield x equals a1 cosine square root of minus c times x plus a2 sine square root of minus c times x, and our t of t will equal a3 e to the ct. Plugging in our first boundary condition will yield 0 equals x of 0 t of t, which equals a1 a3 e to the ct, which, since a3 cannot be 0 again, implies a1 is equal to 0. Okay, now using that in our second boundary conditions, we'll say 0 equals x of 1 t of t, which equals a2 sine square root of minus c times a3 e to the ct. There are two possibilities here. We know that a3 is not 0, so let's divide by the a3 e to the ct. That implies that either a2 is 0, which will again give us that trivial solution, which we eliminated, or the other possibility will be if the square root of minus c equals n times pi, where n is an integer. Therefore, we can say the only possible non-trivial solution is x of x t of t equals a2 sine of n pi x a3 e to the minus n squared pi squared t, where n is in z. Just solving square root of minus c equals n pi, you square both sides, take the minus sign, and you get c equals minus n squared pi squared. Now this is true for any n in z and for any linear combination for n in z, which implies, finally, our u of xt equals, which we can write, we can combine the negative n's with the positive n's, and we can eliminate n equals 0 because the sign will be 0 there. So we can say that our u equals the sum as n goes from 1 to infinity, a sub n sine of n pi x e to the minus n squared pi squared t. Now one more thing to do. We're going to apply our initial condition. This should say initial condition, by the way, not boundary condition, which says that u of x0 will now equal the sum as n goes from 1 to infinity of a sub n sine of n pi x equals our f of x initial condition. And we'll use our Fourier analysis to find the appropriate coefficients of a sub n. And that will complete our solution. Here ends the video.